Hi, everyone. My name is Nathan Piccini. I am one of the marketing managers at Data Science Dojo, and we're really excited to have Marit Vidman and Corey Wessinger here with us today. They're going to be doing a talk on time series analysis with the KNIME Analytics Platform. So Corey and Marit, why don't you go ahead if you want to do another introduction for yourselves. I know, Marit, we were talking about skipping this slide and just jumping right into things. And then before I actually officially hand it off to you guys, I just want to mention for Q&A, if you're in the Zoom, go ahead and just use that Q&A tab like we normally do. It just helps us keep everything organized. And then if you're on one of our live streams, go ahead and ask your question in the chat and we'll make sure to pull it into the Zoom for you. And we're going to be answering questions at the end of the webinar today. So Corey, Marit, why don't you go ahead and take it over?
Thank you very much. And yeah, thank you everybody for joining. So today the speakers are Corey and I, and we are data scientists at KNIME. I work for the education team, so I'm also giving KNIME courses, for example, the time series course, like Corey is, and otherwise writing books, blog posts for the education at KNIME. Corey, do you want to say something about you?
Yeah, thanks, Marit. So again, also a data scientist at KNIME. It seems like at least one person in the chat's heard of Marit and I before. So glad to see you here. We both do a lot of work with time series analysis and forecasting. Specifically, I do a lot of that with signal analytics as well. And yeah, we've been doing a lot of writing and talking about this topic lately, and we've got a book coming out soon, codeless time series analysis with KNIME. So that'll be coming out later this summer. So I see some requests for correlation analysis and multivariate stuff. So maybe check that out and see if your topics are in there. Yeah, if you follow us on LinkedIn, you'll hear more about that in the coming months. And I think with that, we'll kind of get started.
Yes, thank you. And how do we get started? So today's webinar is a bit about theory of time series analysis, a bit of theory about the techniques, like for example, the Arima Model. And then we will end with a practical application in KNIME Analytics Platform. Corey will show you this part then at the end of the webinar, but here you see already how it looks. So you have a KNIME workflow where you implement the time series analysis and then you visualize the results. And all of this will be available for you then later on the KNIME Hub so that you can inspect and use it also for yourself. And the slides and the link to this workflow is then shared afterwards. Okay. So starting what time series analysis is and why do we use it? And the most common application of time series analysis is to do forecasting of some future values and future quantitative values in this case. And when can we do that? We can do that if we assume that the historical data or the past values are related to the future values. So there is something that we know today and that influences how the values look in the future. And this is true, for example, for the temperature. If it's hot today, then this gives some hint about the weather today because these both days, today and tomorrow, are in the same season of the year. And in addition, the dynamics, how the past values influence the future values, they are supposed to stay similar over time, and so that the forecasting works. And what kind of methods we can use for this forecasting? We have here listed 3 main methods: classical time series analysis methods, then explanatory analysis methods, and machine learning methods. In this webinar today, our focus is on this number 1, so classic time series analysis techniques, but I will quickly introduce all of them here. So the classic time series analysis techniques, they are based on the components or elements that we can extract from the time series and that repeat or describe its dynamics over time. So there is something like a trend or seasonality, and they are all of the same variable. So we use the historical data of, for example, the weather to predict the future values of the same variable, so the weather. And this is called univariate time series analysis. The second approach could be explanatory analysis. And here we don't only use the historical data of the variable itself, but in addition, also some other variables. And thirdly, the machine learning models. This is something that you might know from other data science applications, for example, using a random forest model. And here we can use both the historical data of the variable itself and also these other variables, so similarly to the explanatory analysis when we do multivariate time series analysis. Okay, so this is the bigger picture of time series analysis. And now what kind of data we have then for the analysis? The time series data is characterized by the fact that it's dynamic, so it's collected over time. How is this different from the cross-sectional data? So the cross-sectional data is always collected in one particular point of time. So it's a snapshot of a situation. Whereas time series data, it's collected at multiple time periods so that we have the same object observed in different points of time. So if you think, for example, a survey that you sent to your customers and you want to estimate the sentiment of the customers. If they fill in the survey once this week, for example, then you have and for example, 100 customers fill in the survey, then you have an estimate of the sentiment of the customers in one particular point of time this week, for example, and that's cross-sectional data. But if you send the survey to the customers, for example, every year, and you have this data for 10 years, then you have a time series data of the sentiment of the customers that comes from these multiple surveys. Okay. And finally, we then do the forecasting using the time series data. And what is our goal there? So the goal is to have forecasts of what will happen in the future. And time series analysis techniques is the closest we can get into the estimate of the future, what will happen there. We can start with something quantitative. So here you see on the slide just a quote of a quantitative or qualitative forecast about the market for computers. This obviously now many years later, we saw it went wrong. So we can do better with some quantitative methods, like time series analysis. But also there, we also need to consider that they are not providing the truth if we don't add some common sense in there. So the cartoon here gives an example of bad example of using the quantitative models without the context. So if we have the quantitative models for time series analysis and we use them correctly, then we can get the accurate forecasts of the future and with some estimate also about the uncertainty of the model. This was a quick intro about the theory of time series analysis. And now I would move on to the steps, techniques that we use when we do time series analysis. And the first things that I introduce is how to pre-process the data before actually moving into getting some insights of it or modeling it for forecasting. And these are needed because the time series data that we access, for example, we collect collect the data from customers, or we have a sensor or something else, it's often not clean enough to move directly to data exploration or analysis. So what might be there, for example, is that there are some timestamps missing. And the pre-processing step needed there is timestamp alignment, which introduces the missing timestamps in there, so it makes the time series equally spaced. And here you see an example on this slide of a time series component in KNIME. So many of these time series techniques are implemented as components in KNIME Analytics Platform, and you can use them via their configuration dialogues. And this component, for example, it accesses some data where there are hour-by-hour timestamps, but it's not equally spaced. So in this example, there is, for example, the midnight hour missing, and the component then produces the equally spaced data. So here it introduces the missing timestamp from the midnight in between and populates it with a missing value. The next step would then be to estimate this missing value. Okay. Besides the equal spacing, another commonly used pre-processing step is the time aggregation. And for that, we have the component called aggregation granularity. Why do we do that? Because the level of detail in the time series data might not be the one that we need for our analysis. So maybe we have, again, data hour by hour, like in this example, but actually having daily values is enough. Is enough in one hand, on the one hand, and also it might be very hard to carry the data through your analysis if it's too detailed. So it's too much in volume, and it's maybe showing too much dynamics other than those that you are interested. So the time aggregation works so that you input some data with some granularity, in this case hourly, and then you say, what do you want to have at the end? For example, daily values. And the second thing to define is how to aggregate the data. So do you want to have, for example, the daily average or daily sum or daily maximum? And all these things you can define in the component. And here is now an example from hour to day, but you could do the same, for example, from day to month or month to year or day to year if you want. Okay, this was a quick introduction to the pre-processing, and what comes after that is the data exploration. And when we do data exploration of time series data, then we almost always, and in any kind of time series data, we can inspect three different components or main elements of time series. And these are called trend, cycle, seasonality, and residual. So what are these and how they look like? And actually, a line plot is a very useful tool for inspecting these dynamics in the time series. So the trend is the general direction of the time series. Are the values increasing or decreasing over a longer time period? And is the increasing linear or maybe non-linear, or the same for decreasing trend? And in this line plot, you see an example of some sales value recorded, for example, over 15 months. And you say that in the shorter term, there are some periods when the sales are decreasing and other periods when it's increasing, but overall it's increasing and linearly because we can fit this linear line in there. So this time series has an increasing linear trend. Okay, then the second element, main element, is a cycle. And the cycle is an repeating pattern, but it repeats over a very long time period. So this line plot here shows an example. This is a bit scientific example and not as easy to understand, but it shows the sunspot numbers per month and how it changes through years. And you can see that it reaches a maximum at about every 10 years. So the pattern is repeating with the cycle, with the length of the cycle of 10 years. And this is actually quite difficult to inspect in the most time series that we are dealing with, because often we might have data, for example, for 1 or 2 years, and that's too little data, too short period to inspect the cycle. But in a data with time period of something like 50, 60 years, we can inspect the cycle like this. Okay. The other 2 main elements is then the seasonality and residual. And the seasonal pattern, or seasonality, means that there is in time series a seasonal pattern, but or that repeats over a shorter time period. So here, for example, there is a weekly seasonality because the same pattern repeats every week. And what is this data? So here we have the newspaper sales, and day by day, and here for 4 weeks. And it means the newspaper sales go always up on Monday, stay on a high level through the working days, and then go down on weekends. And such seasonal patterns in the data, they are often related to some human behavior or some seasonality in the nature, for example. And here it could be, for example, because the newspaper is not published on weekends, or the shops are not selling are not open, and they are not selling the newspaper then. Okay, and the last main element is the residual. And this is what is left from the time series if we extract the regular or the other main elements, so the trend, cycle, and seasonality. And often there might be something left, some kind of dynamics left in the residual term, so it's not completely random. And therefore we, for example, model the residual series with, for example, an Arima model. Okay, and this actually brings us now to the forecasting or the modeling part. So we have now the data pre-processing, we have the data exploration, and now it comes to the modeling. There are several approaches also to the modeling. So 2 that I introduce here are the classical decomposition and Arima, and actually Cory will talk more about the Arima in the second half of this webinar. So the classical decomposition techniques for forecasting mean that we use those main elements of the time series that I just introduced also for the prediction. So if we, for example, inspect the trend in the time series, the trend is a linear model, then we can apply the linear model to predict how the time series, for example, the sales value look in 5 years or in the next week, depending on the granularity of the data. Or we can use the seasonality. If we know that the newspaper sales are always high on Thursday, then we can use this information to predict the newspaper sales next week based on the values in this week. And the Arima models, here the approach is a bit different, and the model is a bit more complex because we model the past or the future values based on the past values and past forecast errors. And there is a model similar to regression or linear regression that is modeling this relationship. And I will leave that more introduction to that to Cory. Instead, I show you an example of a very simple model, and this is called KNIME Prediction. Why I show this to you? Because it's actually often good to have some kind of a benchmarking model before you go into the more complicated and more models that require more effort from you for the forecasting. If this KNIME prediction is doing better than your model, then it's maybe also because the data is not forecastable in the way that you think you can do. So this KNIME prediction predicts the future value by the most recent known value. So if we know the value today, the prediction is then the prediction for tomorrow is today's value in daily data. And when does this work? So if the data shows is the so-called random walk, so there the next value is the day value before plus some random error. Okay, and besides having the benchmarking model to see if the forecasting model is actually useful at all, it's also good to consider some other things when you select which model you use. So here on these slides, I have listed you something that you can refer to later in the slides, but I will highlight there a few things. So one thing is the availability of the data. So often the machine learning models, they are able to create accurate predictions if you can provide enough of training data. So they learn from the masses of training data, all the possible relationships, dynamics in the historical data, and generate accurate predictions if it's available. If not, then the machine learning models are often not the best performing ones. Another thing is here the readability or interpretability. So the machine learning models, for example, they are often not as easy to interpret, if at all, compared to the classic time series techniques. So if it's important that you can explain your model, how it's generating the predictions, then the classic time series techniques might be better choice than the machine learning models. And the third thing I highlight here is the deployment frequency and the complexity that it takes to train the model. So sometimes the time series applications require predictions very fast or require retraining the model very often. And if the model is too slow, or if the prediction happens too slow because the model is too complex, then it might not be worth using it, although the predictions are more accurate. Or if we need to retrain the model every day, for example, because the data changes, it's something that evolves very quickly. If it's too costly to retrain the model, then the higher accuracy that we can reach, it might not be worth it just because of the effort to retrain the model. So this was actually the part and interaction from my side, and I would now give over to Cory to talk more about the Arima models.
Okay, thank you, Marit. Yeah, so one of the big reasons that we talk about this slide here, the which model slide, is to kind of make sure that you motivate your time series analysis project according to some actual need, right? If all I need to know is how many newspapers am I going to sell tomorrow, and I don't need to know how many I'm going to sell next week, maybe using that naive forecast here was a great solution, because typically when we have a very short forecast length, the naive prediction performs very well. If our data is incredibly random and doesn't seem to have any kind of pattern in it, which is frankly possible, then a mean value prediction can be very effective. So it really depends on what we're trying to accomplish with our forecasting model when we go and we start picking how to do modeling. When we start talking about needing to generate longer forecasts, especially if we need to do that without having tons and tons of past training data. That's when these Arima models start becoming very useful. They can generate longer length forecasts than these basic techniques like the naive prediction. And they can do that without substantial amounts of training data. Now, before I get into those, I kind of want to address one question here. We will have a Q&A section at the end. So for the most part, we'll get to those questions at the end. But there is one question here that's asking about what the difference is between cycle and between seasonality. And because the Arima models are going to kind of incorporate a lot of seasonal patterns, I want to address that really quickly. So cycles and seasonalities are very similar in a lot of ways. So at first glance, a cycle does look a lot like just a longer length seasonality, right? But it's a little bit more specific than that. When we talk about seasonalities, typically they're shorter length, short enough length that we're able to actually model them when we're doing our forecasting. That's one feature that's true. But the other thing that's true about seasonalities is that seasonalities by definition have a finite length. They're always the same length. So we could talk about a daily seasonality, and it's always 24 hours every time. A day is never 25 hours. But if we go back and we look at the sunspots line plot, let me go back and actually bring that one up just a second. It'll be a little easier to talk about. Oops. Here we go. When we talk about this sunspot cycles here, they're not all exactly the same length. Like some of these could be 5 years longer. Some of them could be 5 years shorter. So that's a feature of cycles that is totally different than the feature of a seasonality. They're not always the exact same length. So that's something to keep in mind. And that means we model them in very different ways. Another thing about cycles is that typically they are very long term. So it's pretty rare to actually go through the trouble of modeling cycles. Because typically we just look at these shorter windows of data and we just kind of look at the local behavior of that cycle and treat it like a trend line. So if that cycle takes 20 years, but we're only analyzing 6 months of data, we can pretty much ignore that cycle completely and it'll fall into the trend. So another good way to look at cycles is as evolutions of the trend. So the trend is upward for a while, and then it's downward for a while, and then it's upward for a while. And typically we model these cycles just with a trend line, because typically we look at small enough windows of the time series that they don't change much. So depending on what you're modeling, of course, that changes, but that's the difference between cycles and seasonalities. Cycles have variable lengths where seasonalities are always the same length. Okay, so for the second half of the session here, we're going to introduce the Arima model. This is a model that I really frequently recommend when you're trying to generate forecasts on data that's got these seasonal patterns in it. Maybe it's something daily, maybe it's something weekly. So that could be like one of our favorite examples for forecasting is things like temperature data. Like that very clearly goes on a 24-hour pattern, right? It's always hottest in the middle of the day. Or things like electricity consumption, because you use more during the day when you're running your air conditioning, maybe use more in the summer. And again, those are seasonalities because they're 24 hours or 365 days, and they kind of stick to that length. But a lot of the times we might even not worry about that annual seasonality. We might let that bake into a trend line if we're looking at a short enough data turn. So that's one of the strengths of these Arima models, is that we can generate multiple patterns worth of forecasts. So if I'm looking at daily seasonalities, I can generate multi-day forecasts with only a week or two of data even. So usually my rule of thumb for using the Arima models is have at least 3 repetitions of your expected pattern before you try to model it with an Arima. Now, if you've got 2 years of hourly data, you can certainly move on from the Arima to something more complicated like an LSTM, or even just trim that data down and just use some of the more recent data to fit in Arima model. So these models work particularly well when you don't have tons of data that you need or available to train. So the first thing to introduce is kind of the general framework of the Arima. What is it? Looking at the name of it, you notice it's all in caps. That is because it's an acronym. So there's 3 sections to it. You can kind of see those down here. The AR stands for autoregressive. The I in the middle stands for integration, and the MA at the end stands for moving average. So the Arima is kind of like a regression model, except we're not regressing against like the date or some independent variable. We regress against past values. So it's autoregressive in the sense that it's regressed against itself. So we have this regression model that tries to predict tomorrow based on yesterday and the day before, for example. So in that sense, it's autoregressive. Now, to use the Arima, a few different things are required. It does have some statistical requirements that you might not be familiar with if you're used to using popular models like the decision tree that can pretty much be thrown at anything with good success. To use the Arima and the Sarima, which is its seasonal counterpart that we'll introduce in a couple slides, you want your data to be stationary. So what it means to have stationary data, I'm going to steal a graphic from a previous slide again, is to have something, in this case, we're talking about weak stationarity, just to clarify, is we're talking about something that has constant mean and constant variance. So in this case, we can see quite clearly that this residual has constant mean, because if I kind of imagine myself fitting a trend line through it, it would be flat. So that's one requirement. The other requirement is that we have constant variance. So it looks like it jumps around a little bit more over here than it does over here. So it doesn't actually have to have a constant amount of calculated variance as we look through the data. Keep in mind that when we say this, what we mean is that whatever distribution that this data is truly sampled from, it has the same mean and it has the same variance over time. So that's a little bit different. It's okay if that variance fluctuates a little bit as you go through and approximate the true value of it. But we see that it's mostly jumping around the same amount. It's mostly flat, and that's what we're looking for before we can use the Arima models. So sometimes you handle that separately from the Arima. You could do that by differencing your data. You could do that by lagging your data. You could do that by detrending it, by fitting a linear regression through it and subtracting that out. So there's different ways that we can do that. There is one way that we can stationize our data inside the Arima model, and that's this integration portion. So we'll get to what these different terms mean in the coming slides, but those are kind of the 3 core sections of the Arima model, is that we build this autoregressive model, and we do some integrating there to get our data stationary before we do so. So this is what the common notation for the Arima looks like. So this is for a Sarima, actually. So that'll be a seasonal Arima. And the way that works is we have these 7 different hyperparameters that kind of configure the model before training time. And we'll go into these one by one, but really what we have here is 3 that are the core terms from the Arima, and then they've got 3 more that are seasonal versions, as well as this S, which symbolizes the length of the seasonality. And then these are just the PDQ. So you'll see us using those letters a lot. The lowercase ones are the regular ones, and the capitalized ones are the seasonal ones. So the first part of the Arima model is the autoregressive part. And down here in the middle of the slide, you can kind of see an equation for what that looks like. It should look fairly familiar if you've seen regression models before. We've got our dependent variable over here. In this case, that's y sub t, the tth entry in our time series. And then we have our independent variables back here, which are t minus 1, t minus 2, etc. So that's what it means, again, to call this autoregressive, is we're building a regression model on the series itself, so on these past values of the series. So that's what this part is. It's pretty straightforward. We're just using usually like something like MLE to fit these coefficients and build this regression model. So that's an autoregressive model, and that's just the AR part. You'll notice down here that we have a variable. So this is P, and it's called the autoregressive order. So this is the order of the, this is the number of terms that we include in this autoregressive portion. So when you go back and you're configuring the Arima and you say, I want my p-value to be 3, then that means you include yt minus 1, yt minus 2, and yt minus 3. So that's what we're configuring when we go through and set up the Arima models. It's really just how many terms we include in these different portions of the regression model. So a p-value of 3 would just mean the past 3 values get included in the regression. Okay. The other half there then is the moving average portion. So it's easy to mix up the moving average here with something like moving average smoothing, where you run a window across your time series and do something like take the average inside of each window to kind of smooth out all the spikes and bumps in a time series. So this is not that, but it has the same name. So just be careful not to get too confused with those if you are looking them up. This is a moving average model. So try searching that if you choose to look it up more. And what we have here is something really similar to the regression model that you saw on the previous slide, where we use this term Q, and that's just the moving average order of the Arima model to determine how many values we include in this regression. So if I say my Q value equals, let's say 3 again, then I'll use epsilon t minus 1, t minus 2, and t minus 3. So that's just how many terms that I'll include. The difference here is, though, that these epsilon t's aren't past values of my time series that I'm trying to forecast. These epsilon t's are past forecast errors. And that can be a little bit tricky when it comes to actually writing the training algorithm for, but we don't need to worry about that too much right now. The idea here, though, is just that we capture these past forecast errors and use them as inputs to our regression model. So it's kind of intuitive to understand why these autoregressive terms are useful when we're trying to build a forecasting model. If I know what the temperature was 5 minutes ago, of course, that's going to have a huge impact on what the temperature is right now, because it only changes so fast. So that kind of makes sense. When we're talking about how many moving average terms to include, or why we want to include moving average terms like this with these past forecast errors, the main benefit that we get out of doing something like that is that we build in this ability to respond to spikes in our data. Like, let's say I'm forecasting the temperature and everything's great, everything kind of moving, it's slowly cooling off as we get into the evening, and then all of a sudden a thunderstorm rolls in and my temperature goes way down. This gives the model the ability to respond to unusual events in that way. So pulling those two different equations together, over here we have the autoregressive component, and over here we have the moving average component. So we bring those together and we get the regression model that represents the Arima. And up here we just call it the ARMA, and that's because there's no I part yet. We haven't really talked about the I part yet. So the I is for differencing. So when you're training an Arima model, a common way to induce stationarity is to difference your data. So differencing your data is when you take every value and subtract from it the previous value. So you might remember doing something kind of like this in an introductory calculus course where you're kind of approximating derivatives and stuff like that, maybe. We're looking at rates of change. So when we difference our data like that, it helps remove trends, it helps remove seasonal patterns, depending on the kind of differencing we do. And that's what that I stands for. And that is controlled by the D term. So you don't see that D term, well, it's down here on the slide, actually. That just determines how many times we apply differencing. Now, the next question kind of becomes, how do I choose my P's and my Q's, right? How many autoregressive terms do I need to include? How many moving average terms do I need to include? is you really don't want to include too many because your model will take longer to train, you'll overfit. There's lots of reasons not to include too many parameters in a model. So we just kind of want to make an intelligent choice. And the way we do that is by looking at these two plots. So there's two plots here, the ACF plot and the PACF plot that you see on the sides. The top one is the autocorrelation function. And what this one does is it looks at, on one axis, so it looks at the correlation between our time series and lagged copies of itself. So let's say we've got my original time series, I'll just call it YT, and then we've got a second copy of my time series that's YT minus 1. So every value in that second copy is just the previous one. If I look at how strongly those two series correlate, so just like Pearson correlation, I get a value. And that is this value right here. So I don't know if you can, I hope you can see my mouse, but it's this value here where 1 would be on the x-axis. So we can see that with this data that we're working with here, which is actually taxi demand in New York City, that the correlation between now and 1 hour ago is very high. And that's really common to see in any kind of data that's continuous, anything that doesn't just jump around randomly. If it decays slowly, or even if it decays quickly, we usually see a lot of correlation with now and 1 minute ago, right? These things are continuous. Down here, we have the partial autocorrelation function. So this is really similar to the autocorrelation function. It also plots correlation versus the number, the lag distance that we compare it to. So if we're comparing it to just YT minus 1, or if we're comparing it to YT minus 40. But what this one does is it removes the effects of serial correlation. So for example, if I'm correlated with 1 hour ago, and 1 hour ago is correlated with 2 hours ago, then I'm automatically going to have some correlation between now and 2 hours ago. And what the partial autocorrelation function does is it tries to remove those effects. So there's a whole long equation for how that serial correlation is removed, but that's the idea here, is that we can kind of just see how much correlation is because this term correlates with now, and how much of it is just because it correlates with t minus 2, which correlates with t minus 1, which correlates with now. And these are the two plots that we'll use to look at our P and Qs. So I'm going to move on to the next slides where we'll talk about those specific hyperparameters and how to use these plots. Okay, so the general rules for kind of identifying the model parameters here. So I'm actually going to go back here again, just because I've got the plots. And when I'm trying to pick the p-values, so again, my p-value is the number of regressive terms that I include in my model. So that's YT minus 1, YT minus 2, YT minus 3. How many of those do I include? I'm going to use this partial autocorrelation function plot. And I see that right down here. I've got one term where it correlates really strongly with now. So I'll probably just use one past value in this time series. But sometimes it takes a little bit longer before that decays down to zero-ish. Another notable thing that I see looking at this partial autocorrelation function is that there's a spike way down here. So this is actually about 24 hours, this spike down there. And that is a good way to tell that we've got not just correlation with an hour ago, but a correlation with 24 hours ago. And again, that makes sense. Because again, this is taxi demand data from New York City. And it makes sense that people are typically ordering more taxis at 8 a.m. Than they are at 4 p.m. So there's a lot of relationship with taxis ordered now and taxis ordered at the same time yesterday. So there's kind of those two spots. So what we're kind of doing is walking through here, looking at all of these lag terms and saying which ones of these correlate with my target. I'm going to use those ones as inputs for my model. So I really just see the one term here, and then I've got a term here at 24, and then I've kind of got another one around 48 over here. So we'd play with that a little bit more and see what we want to use. But that's kind of the idea, that I'm picking out these spots on my lag axis and saying, I want to include those as inputs to my model. How can I do that? And then talking about the autocorrelation function, this is typically the plot that we'll use when picking those Q values, when determining how many past forecast errors to use. So I see on this one, it goes down to 0 again pretty quickly. So maybe I would just include 2 or 3 values here. And when I include 2 or 3 values from this one, I'm talking about Q. So my P values come from the PACF and my Q values come from the ACF. So I see this dropping fairly quickly. And I see this one kind of decaying a little bit more slowly. So I might again include a couple of values of Q. So looking at these ACF and PACF plots, the PACF decays very quickly, but the ACF does not. So I'd probably just use 1 or 2 values for P, but maybe a few more, maybe even like 3 or 4 for Q values up here. And you might look at this and say, well, what if I use like 10 for Q? And you could certainly try, and you might see that there's correlation far enough out to make that useful. But I typically avoid using terms higher than 5 or so in these models, just because I haven't seen a lot of great return. You start struggling with some overfitting, you start struggling with train times and things like that. Okay. So just to kind of recap a little bit here, some model identification stuff. So if I have an AR1 model, so just something that has, I just think has a bit of autoregressive stuff going on. So this would be an exponential decay. So right now is exclusively related to the previous value. That's it. So that's your classic, trying to remember the famous first problem in diffeq. That's your famous differential decay, exponential decay problem, though, is when your only thing that your rate of change is related to is the previous value. So we might see that here with more than one value as well. So we might have multiple peaks. We kind of maintain that. Oops, let me go back to my slide. Here we go. We kind of maintain some of that autocorrelation in the PACF plot for multiple terms. We'll start using more values for P. If you're looking at an MA1, then you'll see a peak here on the ACF plot, and then it'll kind of go down. So we're kind of comparing these descriptions of the ACF and PACF plots to when you'd have an MA1 or MAQ. So we see here, let's go back to it for a second. So we've got peaks at lags 1 up to Q, and then exponential decay of the PACF. So we see here that we've got sinusoidal peaks, and those continue to happen. And then we've got the decay here in the PACF. So really what we see is a lot of a pretty high value for Q, because we've got 1, 2, 3, 4, 5 peaks, and they're kind of staying fairly high correlation. So you kind of have to decide on your own which ones of these terms you want to include. I might just include 2, maybe 3, because after that we're below 0.5 correlation, and it may no longer be worth including. So keep that in mind when you're choosing the Q value. Is there's going to be some correlation between those values and the target, but you don't have to include everything just because it correlates a little bit. You can just kind of take the important terms and include them and see how that goes. So again, here's just some more examples of the ACF and PACF plots. So here's an AR2. So we're looking at the ACF plot, and it kind of just decays slowly, but we have 2 values with high correlation on the partial autocorrelation plot. So I see these 2 spikes here, so that means my p-value should be 2. And then down here, it's just another example where I've got a p-value of 2. I see my decay in the ACF plot, but I see 2 spikes here in the PACF plot. And the thing I want you to take away from this is that it's okay if these 2 spikes aren't both positive. A negative correlation is still a strong correlation. Another example with the moving average, we look for a decay in the ACF, but we look for spikes in the, we look for a decay in the PACF, and we look for spikes in the ACF. So you see there's just one spike here. So we choose 1 for our Q value, right? Okay. Now we've kind of done that for the regular Arima model, but we can also do this with another type of model called the seasonal Arima. So you'll see this abbreviated SARIMA a lot. And this is where we add those other 4 parameters here, the capital PDQ and the S. And these are just going to be the same things, except we look at everything we've talked about prior in terms of these seasonal lags. So we'll look at like a seasonal ACF or a seasonal PACF, where we're looking at spikes here at 1, another spike down here, another spike down here, etc. So if we had a 12-hour seasonality, and we had these spikes every 12 hours, and I see maybe 2 or 3 of them, then I'd use 3 as my Q, my capital Q value here, because I see 3 strong seasonal spikes in the ACF. Same thing with capital P. If I saw 3 strong spikes in my PACF at those seasonal intervals, then I would use that value again for the capital P. Okay, and then just to kind of recap that, and we'll share these slides so you can review them as well. The first thing we want to do is obtain a stationary series, and we usually do that by differencing. You can do that inside of the Arima model by setting a value for I, which will determine the number of times that you difference your data. If you have your trend, differencing it once is usually fine. Differencing it twice will help you deal with quadratic trends and so on. So then we need to figure out the orders here. We find our P values by looking at the PACF. And we find our Q values by looking at the ACF. And again, we're kind of looking at how long those values stay high for. So we want to incorporate those correlations into our model. And then we kind of run these models and we look at their different scoring metrics and see how they've done. It's common practice to kind of, if you think that your Arima configuration should be like 213, to kind of wiggle those around a little bit. Try 213, try 113, and kind of compare them because it's not the hardest science here when we're talking about picking these hyperparameters. Although typically following these methods will give you a model that you'll be happy with if the Arima is going to work out well. Okay, and then this is just another more in detailed step-by-step for finding those hyperparameters. To train these Arima models in KNIME, we have another component available. It's called the Arima Learner. So it'll let you kind of configure all 7 of those hyperparameters here. And if you want to train a regular Arima, you'll just be using these top 3. If you want to train a seasonal one, you'll be using all 7. And then, of course, there's a predictor that goes with that generates forecasts. Beyond the Arima and some of the components that Marit's introduced, we also have this additional suite of time series related components for things like data cleansing, or we can use something like the Fourier transform to convert our time series data into cross-sectional data. That's useful if we want to perform, for example, a classification problem on a signal. Okay, and I do have a demo if we have time, but I want to run through the questions first, and then I'll show you what a quick workflow would look like here. So the first question that I see here is, how would you apply your techniques at the millisecond level? Well, my answer to that question is that I wouldn't use the Arima. If I was looking to generate forecasts for a very high frequency time series, maybe something where I'm looking at having hundreds of thousands of records, I would not use the Arima model. I would look into doing something, if you have the capability, I would look into doing something with an LSTM, for example. That would be a good place to start. Or even building other kinds of regression models, like maybe building a model with some Fourier terms, for example, would be interesting. It really just depends on what the data is. But if you've got a really large data set, I would avoid the Arima models because they don't really scale up well to large data sets. They take a long time to train. And again, the Arima isn't going to perform very well if you do have a long enough time series that you're trying to model multiple cycles out, because these Arima models only incorporate seasonalities, which is cycles with constant lengths, right? So if the length of your repetitive patterns changes, the Arima model isn't going to be able to capture that. And the reason why these Arima models only work on constant lengths is because we're building this regression that's based on these specific number of lags, right? So one of the inputs to my regression model might be YT minus 24, so the value yesterday. And if suddenly I'm not correlating with 24 hours ago, I'm correlating with 25 hours ago, it gets a bit trickier to incorporate that. And the Arima models don't work with that. Another question about whether these things apply in other tools. We do have the functionality to do everything we've talked about today in KNIME with these components that we're showing right now. But of course, anywhere else that you choose to apply the Arima, it's gonna be the same. Lots of people like to use the forecasting package in R for this. I'm a fan of stats models in Python. Yeah, so this kind of carries over to any tool you choose to use Arima modeling techniques in. Yeah, so I see one more question that looks like it's easy to answer here. What if our data set is already stationary? If that's the case, you can just use a 0 value for the I, and in this case, you don't perform any differencing inside of the Arima model. So sometimes I just let the Arima model do the differencing itself. One of the reasons why I like to do that is because most packages will undo that differencing before generating the forecast, which just makes it easier for me to build my data pipeline. If I can just allow that differencing to happen right inside the Arima object, whatever that happens to mean, and it's just a little bit cleaner. Yeah. Another question here looks like some recommendations for other models to use. Those are good choices when working with super high frequency data as well, and might be better at modeling cycles if that's something you need to do. Okay, I'm gonna close the slides here in a second, but I have one more thing I want to show you. So you'll get these slides after the presentation, but if you're interested in this and are interested in trying it out in the KNIME platform, we definitely encourage you to just go to our website and download KNIME. It's just an open source tool. It's free to download and use with no restrictions. You can just go for it. And we also have this book code, so you can use DS-Dojo-0522, and you can use that to download any of our books on the KNIME Press for free. That book code will last a month or two, so if you're interested in using that, by all means, grab that book code, go to knime.com/KNIME Press, and you can check out some of our books. We've just put a few of the examples here on the slide. For more time series related content, Marit and I are just finishing up writing a book called Codeless Time Series Analysis with PACT, and that'll be coming out in the next few months. So if that's something you think you might be interested in, grab our LinkedIn profiles from, I think, the second slide, follow us, and you'll definitely hear about it. All right. And I'll stop my share now.
All right. Well, thank you, Corey. Thank you, Marit. It was nice having you today. We'll make sure to have that recording done and with all of the links that you shared with everyone, including the slides. I know a couple of people have been asking for the slides during the presentation. We will have the slides for you. It'll be with the recording under the resources tab. All right, and so with that, we do have a webinar next week. It's a JavaScript for cancer prevention through early detection. It's on May 25th at 9 a.m. Pacific, so a little earlier than we normally do, but we hope to see you all there. And I think my team will also post the link to that. So if you want to RSVP to that ahead of time, please go ahead and do that. So thank you, Corey. Thank you, Marit. Really appreciate you being here with us and explaining time series analysis, especially with the KNIME platform. Make sure everyone, if you need that code, that I think it was DSDojo-0522, go and check out their books. I'm sure they're great. So thank you all for joining. Thank you, Corey. Thank you, Merritt. And I hope to see you all next week.
Thank you.
Thank you. Bye-bye.